Hello students, this is Hydraulic Engineering for Friday the 25th of January, class number 5. Just to remind you of a couple of announcements I mentioned in Wednesday's class, that we're going to have a quiz on Monday, and that will be mainly to assess whether you were able to watch these recorded lectures. Give you an incentive and a reward for watching them, besides the reward of knowledge. Homework 1 is due on Friday by the close of business. Please slide your assignment under my office door before they lock the building on Friday. And we'll have a quiz on Monday that I've already mentioned, and the coverage will also include some of the topics from the homework assignment that you're going to be submitting. So today's lecture, we're going to continue talking about how to find the friction factor F and also apply that new and improved understanding of pipe friction into sizing the diameter of a pipe. You know, when we know what a head loss is going to be and so forth, how to know what diameter of pipe to size. The Colebrook equation's a little bit hairy, right? It's an implicit equation. We have to go back and forth between guesses of F values to solve it. It's not so bad if you're able to type the equation into Excel without messing it up, and I'm actually glad that I messed it up as I was giving that example, because I showed how easy it is to put a parentheses in the wrong spot and then get the wrong value from it. And I'm sure that everyone's seen that for themselves, putting in parentheses in the wrong spot. But anyways, the Colebrook equation being implicit leads to a required iteration to find the F value. Thank goodness there's the Jain equation. The Jain equation, which is on screen here, is a simplified method for finding the F value where it's explicit. The F value is only on the left-hand side of the equation. It's valid under a pretty wide variety of criteria, not quite like Colebrook, which is always valid, but the Jain equation says that as long as the relative roughness, K sub S divided by D, is between 10 to the minus 6th and 10 to the minus 2, then we're okay. And we also have to have Reynolds number of between 5,000 and 10 to the 8th. As long as those two criteria are true, then we'll get a good estimate of the F value. Let's try it out. Let's substitute the same values from the previous example into the Jain equation using a pen cast.
This example has to do with the Jain equation. The nice thing about the Jain equation is it's explicit. Unlike the Colebrook equation, which is implicit, meaning that the F value that we're trying to solve is on both sides of the equation, nice thing about Jain is that the F value is only on the left-hand side of the equation. So I'm writing the Jain equation here. It's still, like the Colebrook equation, has two primary terms. There's the term that has to do with the relative roughness, and there's the term that is having to do with the flow conditions. Okay, so the relative roughness term and the term having to do with flow conditions. As with the Colebrook equation, when you've got a really large Reynolds number here in the Jain equation, this term is going to tend towards 0, and all that will matter is the relative roughness K sub S divided by 3.7D. Don't miss the D, that's a really important part. So the relative roughness term is what governs flow in fully turbulent conditions, as we've seen on the Moody diagram in the past. So we're going to take a look at the same example as before. You remember the trouble we went to, the left-hand side, the right-hand side, using Excel and all that, in a pipe where we knew the relative roughness, 0.15 millimeters, we knew the diameter was 136 millimeters, and we had a Reynolds number of 1.872 times 10 to the 6th. You know this. Let's substitute that into the Jain equation and marvel at how much simpler it is to use, as long as we are under the conditions that it is valid. It is quite convenient. 0.15 millimeters divided by 3.7 times the diameter. plus 5.74, the Reynolds number of 1.872 times 10 to the 6th to the 1/9 power, and then we square all of that. Okay, we will put that into our calculator here, and 1.325, 0.15, 3.7, 136. Okay, so this term right here is 2.981 times 10 to the minus 4th. Okay, 1.872 times 10 to the 6th for our Reynolds number. We take that to the 0.9 power, 5.74 divided by that, and this term is 1.3 times 10 to the minus 5. So you get an idea of the relative importance of each. So we are taking the logarithm of 2.981 times 10 to the minus 4, 3.11 times 10 to the minus 4, and then we're going to square that, and then 1.325. Okay, so 1.325 divided by, I'm going to take the logarithm of that, 3.11 times 10 to the minus 4th, natural log, square it. Natural log was negative 8.075. Squaring it gives me 65.2121. So now, finally, 1.325 divided by the previous, 2.03 times 10 to the minus 2, so that is 0.0203, which is exactly what we got when we were solving this using the Colebrook equation. So Jain is a very nice simplification, as long as we're using it under the range that it's intended, where the limits are K sub s to d ratio must be between 10 to the minus 6th to 10 to the minus 2. So let's see if we satisfy that. Our K sub s to d ratio is 0.15 millimeters, and our diameter 136 millimeters. So that is 0.15, 136. Okay, we are at 1.1 times 10 to the minus 3. So we're good. We're in that range, although we're getting close to the upper range. And then finally our Reynolds number, the Reynolds number limit must be between 5,000 and 10 to the 8th. And our Reynolds number here of 1.9 times 10 to the 6th, we're okay. So we're valid. We're valid with the Jain, and we prove that to ourselves because we get the same answer with Jain as we did with Colebrook.
This semester you can use the Jain equation in your homework assignments, in quizzes, exams, unless I specifically tell you to utilize the Colebrook equation. So you need to know how to solve the Colebrook equation, but for simplicity and time savings, I'll allow you to use Jain unless I'm testing to see whether you can do Colebrook. So here's the Moody diagram, and the Jain equation and the Colebrook equation, those two terms that are inside the natural log here. There's the K sub s to d ratio, where once you get a big Reynolds number, so big Reynolds number looking down here at the x-axis is where this becomes relatively flat. All that matters to find the f value when you've got a big Reynolds number, when Reynolds number is big, the denominator overwhelms the numerator and this whole expression becomes 0, so all that matters is K sub s to d. So this rough turbulent zone is what dominates in the Jain and Colebrook equation with a big Reynolds number. But when the Reynolds number is relatively small, on the left side of this transition zone boundary, then we have smooth pipes that you need to calculate the Reynolds number by considering both terms inside the Jain equation. At a certain point this semester, I'm going to tell you to assume rough turbulent flow, because making that assumption makes some calculations easier. But don't assume it until I tell you to assume it, or at least till I tell you all the warnings and disclaimers and checks you have to do to see if it's a valid assumption. But just to let you know, it would be awfully easy to calculate F if you didn't have Reynolds number in this equation, right? All it would depend on is K sub S to D ratio. It would be pretty easy to find the F value if you assumed the Reynolds number was big. Okay, the Blasius equation is yet another method for finding the F value, except for that it's limited to Reynolds numbers below 100,000. So under the criteria that we've used previously, let's just go ahead and try and see how the Reynolds number performs, even though we're outside of that range that it ought to be used.
Here's yet another way to solve for the F value we're going to need. The Blasius equation, valid for Reynolds number up to 100,000. And it's very simple. 0.316 times the Reynolds number to the 0.25 power. Okay, remember our previous K sub S was 0.15 millimeters. Our previous D was 136 millimeters. Our previous Reynolds number, 1.872 times 10 to the 6th. So we're not in the right range to use the Blasius equation. If we were to use it, well, if we did use it anyway, then the F value would be 0.316 divided by 1.872 times 10 to the 6th to the 0.25 power. Well, the result of that would be 0.00854. No, that's not right. We know from our previous examples that it should be 0.0203. So Blasius only works up to a Reynolds number of 100,000.
We're going to be talking about designing pipes, and occasionally you'll know the expected head loss in a flow scenario. Head loss, of course, is one of the terms in the energy equation, and if we rearrange the energy equation such that the pressure head and elevation head at location 1 is subtracted, at location 2 is subtracted from that at location 1, then we know the head loss that's going to occur between 2 points. Let's say that you know the flow rate that has to go through a pipeline. That may be that you've done some population estimates, you know what the flow demand is going to be. For whatever reason, you know what Q should go through the pipe, but what you don't know is how big the pipe needs to be. You know how much head loss can be tolerated because you know how big a tower is going to be and what pressure is needed at someone's house. So you know the head loss tolerance, and you know the flow rate, but you need to design the pipe diameter and choose a material type. So you're going to select a certain pipe, say we're going to use cast iron, but what diameter of cast iron is needed? Well, there is a method for designing the pipe, and the difference between design and analysis is that in design often we're having to iterate back and forth to find the optimum condition, whereas in analysis it's less common for us to iterate. And of course, in design, the reason why we iterate is we have responsibilities as designers to be efficient. In analysis, we're just sort of saying what the conditions are. In cases where the diameter of the pipe is unknown, we're going to utilize the Darcy-Weisbach equation by inserting it into the energy equation. So a accurate but a little bit more difficult method that's implicit to find the diameter needed we've got a lot of different pipe diameters, is that we're going to start off by assuming some F value. And the range of plausible F values is from 0.08 to from 0.008 to 0.038. So you assume some F value and find out using this expression, which is inserting the Darcy-Weisbach equation into the energy equation. For that guess F value, what diameter is needed for a certain pipe length in meters, flow rate in cubic meters per second, head loss in meters, g is gravitational acceleration, and pi, 3.14159 squared. We find out what diameter. Now that's just based on some guess F value. So what we need to do is check and see, is that guess F value that we selected reasonable? So once we know the D, we can find the Reynolds number by the known flow rate, dividing it by the cross-sectional area, and that will give us the velocity. And then with the velocity, we put it into the Reynolds number equation. Once the Reynolds number equation is found, then we can go to the Colebrook expression, or the Jain equation, and find what F value is it really. We guessed some F value to begin with. We just had some guess F value, but now we calculate the real F value, and we use that new F value in a second iteration of finding the diameter that's required. And so you keep going through this process of you pick some F value, fine-tune the F value, and the D keeps changing a little bit, but the increments of its change will be getting smaller. It will eventually converge. The D value will stop changing, the F value will stop changing, and that's how you know finally that you've got the numerically correct solution for what pipe diameter is needed. So we'll illustrate that principle with an example. In this example, we have a pipe length of 40 meters, and we need to know what diameter of cast iron pipe is required in order to get 300 liters per second to flow through that pipe. So our process is going to be to assume some F value, calculate the diameter associated with that, and then, once we know the diameter, calculate a Reynolds number, relative roughness, and then find out, check what's the F value. Is it equal to what we had assumed, or do we have to find a new updated D with this check value of F? So we're going to repeat it until finally the changes of F and diameter are very small.
Okay, in this example we're going to be looking at trying to find for a pipe length of 40 meters and cast iron pipe with a K sub S value of 0.26 millimeters. We would like to have a flow rate of 0.3 cubic meters per second, and so what diameter is needed in order for that to happen? Of course, remember from the basic principles of energy loss that the smaller the pipe diameter, that means that the velocity is going to be high and there will be more head loss. And so by rearranging the Darcy-Weisbach equation substituted into the energy equation, we come up with this expression: D is 8LQ squared over H sub F G pi squared times F to the 1/5 power. There's nothing mysterious about that. It's simply the Darcy-Weisbach equation, continuity equation, and the energy equation all rolled up into one, where we're trying to find for some F value what the diameter should be for that pipe. In this example, we know that the H sub F is going to be 45 meters. That's how much head loss can be tolerated through this pipeline. So our process here is to start off with a guess value of F. So assume or guess F is 0.015, just as our first try. Okay, so we'll substitute in the values into that equation. 8 times 40 meters, our flow rate 0.30 cubic meters per second, squared. The head loss is 45 meters. G is 9.81 meters per second squared. Pi squared. And then this guess value of 0.015 to the 1/5 power. Okay. So what diameter would be required for that? We'll pop it into our calculator. The diameter that would be needed is 0.1582 meters. Alright, well, if that's the diameter, then our area is going to be 0.01966 meters squared, just by using area is pi d squared divided by 4. And if that's our area, we can find the velocity of flow. And the velocity is 15.26 meters per second. And if we know the velocity, we can find the Reynolds number. And the Reynolds number, 15.26 meters per second. Diameter that we've just selected, 0.1582 meters. And why are we doing these calculations? Well, it's because we started with a guess value of f, and we're testing to see if that guess is accurate or not. Okay, our Reynolds number in this situation would be 2.414 times 10 to the 6th. So let's put all that into the Jain equation to find out what f value is corresponding to these conditions that we've just invented here. And if the f value matches the f value that we guessed, then we are incredibly lucky, and we get to quit doing calculations by hand. But, more likely, we didn't guess the exact right f value to begin with, and so we're going to have to iterate. And our diameter here is 158.2 millimeters for this pipe. By the way, the case of S is 0.26 millimeters in this example. And 5.74, the Reynolds number 2.414 times 10 to the 6th to the 0.9 power. Square that. Okay, the f value, if we do all those calculations, and I encourage you to pause this as needed to do the calculations yourself, 0.0224. So that does not equal the 0.015 assumed. So what do we have to do? Well, in our next round of calculations, we're going to use the same formula as we did before, but we have a little bit better guess of what the f value is. So we're going to use that improved guess of the f value. So the d will be 8 times 40 meters. I guess I should have found the intermediate quantity of all this, because none of that's changing as I change the f value. Squared divided by 45 meters. 9.81 meters per second squared. Pi squared. And 0.0224 to the 1/5 power. Okay, with this new guess value of f, then the diameter that would correspond to that, 0.1714. Okay, so I can calculate a new area that corresponds to that diameter. I can use the Q equals VA relationship to find a new velocity. New Reynolds number I can calculate. And we'll want to see how well does that match up. So then I'd find a new f value using this same equation here. I'll save you the suspense. The new F value, when I substitute in all of the additionally known parameters, if I put in the new Reynolds number, that is to say the new diameter of 0.174, then the new F value I'm going to calculate is 0.0219. So you can see I'm getting pretty close. My first guess was 0.015, and that jumped all the way from that to 0.224. This is a much smaller change, a smaller adjustment. So if I go through the process again, if I put that into a new D, then the diameter that I'd get there is 0.170 meters. You can tell that the diameter hardly changed from the previous diameter, and then that's going to lead to a new F of 0.0218, and that's essentially converged. We haven't changed between the last guess F value that we put in. So finally we know that we can stop iterating, and that the diameter of pipe that's needed to make these conditions true as described, the way that we get 300 liters per second through a pipeline of 40 meters made out of iron that has a case of S of 0.26, and then ensure that there's 45 meters of head loss, is with that diameter of pipe. And that concludes this example.
There is another approach to finding the diameter of a pipe that's required, and it's an explicit equation, but it's a pretty complicated equation. We're taking expressions to the 4.75 power, to the 5.2 power, to 0.004 power. And so just to give you a sense for how that operates, we have a pencast example of that as well.
Okay, there's an explicit method that doesn't require iteration to find the diameter of the pipe needed, but the equation is so complicated that I don't know, you might just be better off actually iterating. Well, let's go ahead and take a look at how to use that. The expression is, I guess it's embedding Jain equation into the previous D equation, which was the Darcy-Weisbach equation and the energy equation. So 0.66 times K sub S to the 1.25 power LQ squared divided by G H sub F to the 4.75 power plus kinematic viscosity times Q to the 9.4 power L G H sub F, the 5.2 power, all of that to the 0.04 power. And the limitations here is the Reynolds number needs to be between 3,000 and 3 times 10 to the 8th. And the K sub S to D should be between 10 to the minus 6th and 2 times 10 to the minus 2. K sub S, H sub F, L all have units of meters here, and Q units cubic meters per second. Previously, when we were working in the Weisbach equation or the Jain equation, we sometimes leave K sub S in terms of millimeters because we may have the diameter of the pipe in millimeters, but here we need to have it in meters. So we'll need to break that habit for this equation. Well, let's give it a try. For the previous example, when we were working with an H sub F of 45 meters, we had a K sub S of 0.26 millimeters and a Q of 0.3 cubic meters per second. Then, remember from that previous example, we found that previously through iteration we had a diameter of 0.170 meters. So let's see how good this one is. And really what it is how good are we at not screwing up the calculations along the way. 0.66, we're going to have the K sub s in terms of meters, so that's going to be 0.26 times 10 to the minus 3 meters. We need to take that to the 1.25 power. Then we're going to have 40 meters as the length times the flow rate of 0.3 cubic meters per second, and the flow rate is squared. G is 9.81 meters per second squared. The H sub F is 45 meters of head loss. All of that to the 4.75 power. Kinematic viscosity of water is 1 times 10 to the minus 6th meters squared per second. The flow rate again, 0.3 cubic meters per second. This time to the 9.4 power. Length, 40 meters pipe length. G, 9.81 meters per second squared. H sub F, 45 meters of head loss. This term to the 5.2 power, and then all of that to the 0.04 power. Alright, really, in all honesty, I want you to calculate this one. Sometimes we don't when we're watching a pencast. Sometimes we just assume that the calculations are right. But when I do this example in class, about half the class, try as they might, gets the calculation wrong, just because it's complicated to get it in. So we'll see how good we all are. Do a quick calculator rodeo here. Let's see if we can do it. Where to start? 0.66, 0.26, 3 minus. Okay, I'm going to pause this while I do my calculations. You won't notice a pause, but you pause while you do your calculations and unpause when you're ready to continue. Okay, going through all the calculations, I end up with 0.175 meters. On the slide it mentions that this less accurate but easier, so-called easier approach than iterating, this explicit method, usually gives us results within about 5% of the iterative approach, and our iterative value when we did it the long way, getting the F value to converge, was 0.17 meters. And so assuming that is correct, 0.175 and the difference there dividing, then it was about 2.9% error. Okay, so that's an illustration of this other method that can find the diameter directly.
Alright, well, that concludes the material that we need to cover for today's lecture. We've taken a look at a couple of examples for sizing a pipe, and just to reassess these announcements, remember that there will be a quiz on Monday, a homework assignment due on Friday the 25th, so please send me an email, wait@marshall.edu, if you have any questions, and otherwise I hope you have a great day, and I'll see you on Monday.